Okay, thank you so much. On this occasion, I will present to you the model about of green hydrogen that I have development in the second version. Okay, I will share the screen. Please confirm me if you see. Okay.
Yes, we can see it's clear.
Okay, thank you so much. Okay. Um, I will begin with the presentation. So this is the model to determine the LCOH and economic viability of green hydrogen, called H2CEM, hydrogen cost and economic modeling, its name. Okay. Uh, this is my profile. So I am in the energy area. I am the founder president of the AEE Bolivia chapter. So I am very active in many areas, mainly in the hydrogen, green hydrogen areas. So you can connect me on LinkedIn in this address. I am very active all time. I publish the articles, news about of the works in the hydrogen area. So this is the main panel of my model. The H2CM model is focused on determining the cost of production plus compression plus storage in the green hydrogen. Okay, plus economic viability of the project. The scope of the model is analyze all ecosystem science, renewable source, plus electrolyzers plants, plus compression, plus storage. All ecosystem is involved to analysis and modeling in the H2CEM. Panel arrangement is structuring with 5 groups of inputs on the main panel. General parameters, power plant parameters, hydrogen plant parameters, hydrogen supply firming is related to the grid connection for compression plus storage, and the 5 is decarbonization instruments. Okay, the key highlight features are 32 modeling settings. It means that we have 32 options to combine all the supply energy, and the configuration with compression, storage, only production. We have 32 modeling sets. Plus, the CBS cost breakdown structure is very high because it has 59 inputs variables. It's very big and complex model in terms of the modeling 59 variables. Plus, the model output has 73 output data. We have many information of output, and with this information, we can to analyze sensitivity plus take decision. Plus, more than 700 sensitivity combinations. It means that we can combine, for example, all output data with a couple of the input data. So in many combinations, we have around of the 700 sensitivity combinations. So we can screening of the panel. For example, you can see this panel. This is the screen. In short time, I will show you the online application. in this case, please let me the pen. So we can choose the language in this regards. The model works with Spanish and English language. You can choose the language and all change of the language. Okay, so this is a small diagram that indicate one is blue box, two is orange box, three is a green box, four is a light green box, and light blue is a 5. This is the order of the charging of the input data. So we can, once that I have charged of input data, you remember 59 input variables, we can see automatically the diagram of the LCOH only production. So we can do initial investment, stock replacement, fixed OEM, water, electricity, and we have if here are incentive financial items. So we can hear LCOH. So this value we can hear, and we can add the compression capex, compression opex, storage capex, storage opex, and we can obtain the final value of the hydrogen produced, compressed, plus stored. Okay, this is automatically the model show out this diagram. So what can we do with all hydrogen produced? The model give us some idea about the average plant of green ammonia, green methanol, steel, or PTL, synthetic crude oil, that we can to produce around of the, for example, a certain volume of the green ammonia or methanol or steel. It means that I produce and storage some quantity of hydrogen, of green hydrogen. So it gives a good idea what is the application that with hydrogen can we. Diagrams. The model showed automatically 32 ways of the configuration of the diagrams. Okay, for example, this diagram configure photovoltaic plus aeolic plus grid connection for consolidate hydrogen plus water plant, electrolyzer plant, production, compressed, and storage. We can hear the pressure level, for example, in production, 30 bars, in compression, 150 bars, and in storage, 200 bars. Okay, we have 32 ways to configuring these diagrams. So the model shows us a carbon footprint, carbon intensity without REX or compensation, with REX and compensation, indirect generated, offset CO2 used. Okay? So the model shows us the summary. We can create each scenario for analysis. For example, we can create a base scenario plus a scenario 1, 2, 3, and scenarios. So we can to compare each one with other scenarios and what's happening, how many input variables we have changed. So what's happening if we change this input or other this So we can compare and understand what's happening, and it is very useful to take a decision on the viability of the hydrogen project. So we have a panel of the sensitivity analysis. For example, we can choose here around of the 8 output data, LCOH, for example, initial investment, is replacement of stacks, OEM, O&M, electricity costs, IRR indicator, MVA indicator, so payback. We can choose between 8 output data and compare with more than 14 input data. And we can create here a graphic with a curves of the showing that what's happening if can I change some value and how to obtain the LCOH or others output data. Okay, so here we can see a table with the values for each, in this example, installed CAPEX and percent of CAPEX as ITC, for example, which of the value of the LCOH we can to see and analyze here. Okay, this is the CBS cost breakdown structure. It's very robust, it's very complete and complex. So we can here, you can see many variables, very important. For example, we can 2x H2 for hydrogen and for renewable. So other data, important, interesting input data is here with the hydrogen plant parameters. We have, for example, OEM's product. OEMs means original equipment manufacturers. For example, if we need a plant of a hydrogen plant around of the 100 megawatts, and the OEMs has modules from the 30 megawatts, we need for to cover 100 megawatts, we need to install 5 modules of the 30 megawatts each one. Okay, around of the 120 megawatts installed of electrolyzer. Okay, so we can hear water costs, water required, and many data and the financial incentives for hydrogen, financial incentives for electricity, for compression, for storage, grid connection, decarbonization instrument. It means very, I think that is many input variables that cover all scenarios possible in the analysis of the green hydrogen viability. For example, in the diagrams, we have here only production with supply energy configuration as it show. For example, 50-50 photovoltaic and eolic plus grid to consolidate hydrogen. This other is production plus compression. You can see automatically shows the models the value of the pressure, of the pressure. For example, 30 bars, 150 bars, and the other only directly from production to storage included a compression unit kit in the module of the storage. And the most complete, most integrate is this. Is this with the all source of energy renewable, so production plus compression plus storage. We have, as I said you, 32 modeling settings. It means that we can combine all, for example, photovoltaic and wind plus electrolysis plus water. Or we can combine photovoltaic plus wind plus grid plus compression plus storage with electrolysis and water. Okay, just say. We have here the LCOH cost structure and the percentage of the drivers. For example, in these graphics, we can see that electricity costs represent that the 59% of the total LCOH is the most important driver in the LCOH. And initial investment is the second most important variable in the cost structure in the LCOH. For example, in these graphics, it means that 29%. Then, so first is electricity cost. Second driver is initial investment, and the fixed OEM is very small. Stack replacement is small, and water is very, very small incident in the LCOH cost structure. So we can show in this diagram on the tax credit electricity, if we can use this, tax credit hydrogen, and grant configuration. So it means to drop the LCOH. For example, $3.13 per kilogram versus $2.11 per kilogram of the hydrogen. So plus compression, plus storage included compression kit, we can hear, for example, only LCOH means or represents around of the 55% of the total final price of the hydrogen costs. Okay, so we can hear compression capex, compression opex, compression opex fixed O and M, capex, storage capex, compression kit capex, storage opex, compression opex. With this cost, we can add, and we can obtain the final cost of green hydrogen produced, compressed, plus storage. Result cards. You can see here many output data. It is very important for it helps to take a decision, analysis. We can see the best scenario, best configuration. So we can see many issues that we can solve with results cards item. For example, for the hydrogen production at 30 bars, for example, we can show electrolyzer configuration for this example. So we can years of before replacement stacks useful life hours, annual degradation rate. In the power supply and water group, we can see all total installed power, grid connection, grid energy price of the photovoltaic and the aeolic, total energy used by electrolysis plant per year. So energy from the grid used for electrolysis, less than 1% approximately. Water consumer, cubic meters per year, millions of gallons per year. So we can hear the hydrogen cost and economic results. You can MPV, for example, IRR and payback. You can see. So we can data output of compressions model, compression cost US dollars per kilogram, how millions of the capex for compression module, what is the energy used to produce in compression per 1 kilogram of the compression we need in this example dot 89 kilowatts hour of the energy. So similar for the storage module, how many tons of the hydrogen storage, days of storage in turn down, days of storage of nominal production, how much is the cost of the hydrogen stored, dollars per kilogram. So how much is the cost of stored or compressed in the kit compressor, dollars per kilogram. So we have many very important information, not only for the capex and the investment phase. So also it's very important for the operation phase. You can see, for example, use kilowatts hour per kilogram to compress hydrogen. So this is very important data for the operation phase of the plant, because we can manage the efficiency energetic with these values from the factory to compare if in the every day is in the average of the value. So we can show the carbon footprint and the power to X, as I said energy usage and REX. And this is very interesting. As reference, land for the supply of photovoltaic energy. What's happening if you choose our energy supply with a farm of the photovoltaic plant? For example, a typical model of the photovoltaic monocrystalline silicon cells with 670 peak values and 21.6% of module efficiency. We need, in this case, 1,493 modules per megawatts. So we need 1,429 modules per hectare. So 1 plus hectares per megawatt. In total, we need 39 hectares. This is the good idea for the land that we need to install of the plant, of the photovoltaic plant. In acres, in the change units, not only, all is the output results in where we have 79 output data. Okay? A generic case we have, for example, online scenario, and we can create a base scenario. For example, in case of Bolivia, in my country, if today we install a green hydrogen plant, so it's possible that we reach $4.23 per kilogram of the hydrogen. Okay? With these considerations, installed capex dollars per kilowatt of electrolyzers are $550 per kilowatt, and the cost of energy photovoltaic we have $44 per megawatt hour, and if the wind LCOE 55. Okay, with these considerations, with these more important input variables, we can get $4.23 per kilogram. So what's happened? What should be happen to we move from this value to $1 per kilogram of the of the hydrogen. Two issues very important and critical. Drop the value of the installed capex and drop of the value of the energy supply. It is possible in my country. It is possible in your country. It is possible in Europe, in USA, in South Africa, in Africa, in Latam. I don't know. So in each country, so we can review, analyze, study regulatory norms, juridics, as normatives, and technicals, and expansion programs of the power supplies systems, etc. Okay, so we can here to compare scenarios, yeah, and finally we can see the sensitivity analysis. As you say, as I said, we can choose some variables of the output and compare with a couple to input variables, input 1, input 2, and we can choose of the best option. For example, if I want, for example, installed capex, I choose 500, and I want to compare with the solar energy cost, for example, $60 per megawatt hour, we can go up and up to green line and the left to see approximately how much is the LCOH, approximately 3.4 dollars per kilogram. Okay, this is very important graphics to understand the move of the scenarios in the analysis. Okay, thank you so much. So, gracias in Bolivia, in Spanish, thank you in English, and I don't know if it is your language, okay? But I can see now you fastly the software. It really is not a software. This is a model, okay? For example, we can here, this is the main panel. We can choose if I want to English or Spanish language. So we can here, for one is the box, a blue box. We can here, for example, plant economic life, a WACC, oh, okay, and we can see here the results, the graphics with the LCOH on the production plus compression plus storage, and we can here the model, the configuration according that I have chosen in the input parameters. Okay, we can hear the parameters. What's happening? For example, we don't want compression. Only we want directly storage. So we can you can see here from production go directly to storage included a compression kit, but it don't has a compression mode. So only I want a compression, but I don't want a storage. We can go to the model. You can see it's changed. Yeah? Production plus compression, pressure 30 bars up to 150 bars in compression. Okay, so we can make 32 possible scenarios of combination in the development of the analysis. In this sense, we can see the results cards here in where you can see what is the best alternative for the development of the green hydrogen project, okay? From energy supply, plus production, plus compression, plus storage, and the energy supply, we can choose, combine or only, or for example, only photovoltaic 100%, or mixed with wind, aeolic 50-50, 70-30. I don't know. We can see and analyze of the financial indicators, and we can see what is the best option for the project. Okay. Finally, we can hear the graphics of the sensitivity analysis. For example, we have chosen here LCOH only production. So we can choose here electricity cost. For example, you can see with the change of the line in the curves of the graphics, and we change. So we can here change, for example, the input of the couple. For example, we can choose here electrolysis plant capacity. Okay, so change of the curves in the graphic and change of the value of LCOH. It means that it's very useful tool to analyze many scenarios and then find the best scenario for the project. Okay, so this is the. I thank you very much. With it, I have concluded my presentation. So I don't know if you have, please, some question, write it in the chat, please. I am reviewing now, please. Let me.
Yeah, thank you so much for the lecture, Engineer Oscar. There are a few questions in chat if you would like to go through them and answer them.
Oh, okay. Let me please read some questions. I have very interesting questions. For example, the first question: how long did it take to develop the model? This model is the second version. The first version I have released on February of this year, and the first version took around of the 4 months, and the second version is more complex, more complete, around of the six months, and the hard work for the final testing, hard testing, compare benchmarking with other systems, around of the 6 months. Okay. The next questions are how does green hydrogen compare to other storage systems like batteries, hydro storage, and ammonia? So I think we have to remember the hydrogen is energetic vector. Is considered today as energetic vector. What means it? Since hydrogen, we can produce ammonia, we can produce fuel cell battery energy, we can produce BESS system, battery energy storage system. It means the base of the all new emerging technologies, energetic technologies, is the hydrogen. Okay, hydrogen is very powerful for ammonia, for steel, for iron, for PTL, as I showed you. Okay. Another question said here. And where is green hydrogen going to be a viable solution and widely used? So I think depending in what region of the world. For example, in South America, Chile country is the leading with in the 5 most countries developers in the world. Chile, for example, in South America, today is producing hydrogen around of the $3 per kilogram of hydrogen. This is very good. And they plan to release a price of the hydrogen up to 2030 year, up around of the 1.2 or $1.5 per kilogram. In this sense, I think the hydrogen is not the future. I think the hydrogen is the present. And the hydrogen, from my point of view and my experience, not only in Bolivia, if in other country, in Latam, other country, the hydrogen is reconfiguring of the new economies in the many countries in the world. Okay, so I think maybe, I don't know, in your region, in the Arabian countries, in the Europe and the Africa, in the USA, North America, South America, I don't know. I think this is a variable depending of the region of the country, policies, normatives, regulatories, green financing for this project, and the most important point is the state's decisions. In each country, we need to state decisions to the deployment of the hydrogen ecosystems. Okay, next question. Next question here. What level of technical expertise is required to use the tool effectively? I think it is important to know of the middle level of the technical requirement in terms of the hydrogen production systems, storage systems, compression systems. I think this is half plus the level. Most important in this case, I think that is the business vision, ecosystem visions of the hydrogen, and hard skills in the economic and financial and cost engineering skills. So I think this is the main or the most important skill that we need to use the tool effectively and not only use configure parameterizers, modifying, make best ways. I think this is the hard skills as business vision, okay, of the hydrogen, of the green hydrogen, power to X vision. It means what can we do with hydrogen in the timeline? What is the first? What is the second? For example, first we can do boarding of the industry, electrical systems, electromobility, or synthetic fuel. We have to analyze the ecosystems and to make a big strategy. In this sense, I think for developing this tool, this model, and to use it, I think we need mainly hard skills in green hydrogen business. So vision plus hard skills in the cost engineering, technical engineering for the configuring and developing this model. Okay. Next question. What are the best configuration to produce green hydrogen with alone? In my experience, I think the best configuration is to reach two critical issues and variables. cost of energy, you remember it that the cost electricity inside between 50 and 70% of the LCOH cost structure. It is the most important, most incident. The second important is drop down the cost of the installed capex of the electrolyzers. So I think we can find in the market electrolyzers size $600 per kilowatt up to $1,400 per kilowatt. China's, India, Germany industry, I don't know. So we can find a avenue of the price of the electrolyzers. But these two issues is very important for to think to reach in some moment a LCOH competitive with the Greece LCOH with source of the fossil energy. Okay. Okay, here the next question. Are there case studies of example where H2CM has been successful applied to real world project? Okay, in this moment, I am working on two projects in Bolivia for to applying the H2CM model in the engineering studies phase. Okay, so up to this moment, this tool, this model is very useful in the engineering studies phase. For example, conceptual engineering, basic engineering is very useful because the model help us to visualize many alternatives of the viability in the project. Next question. Can the process of compressing hydrogen be more expensive over time if the storage unit loses pressure? It's possible to it. Okay, it's possible. What is the steps? We can produce up to 50 bars in production level. If want to compress, we can to compress up to 150 bars. Okay? Plus, if I want to storage, we need to compress up to 250 bars. Okay? It will increase. So what's happening if I don't have a storage model? So we can to compress up to around of the 200 bars. In this case, it is more expensive. Okay, in this case. The next question. How can someone gain access to the model? In this case, this model is a consultant tool. So if you want to access to see sometimes some graphics, some tips for use, you can join to WhatsApp group that I have. In this WhatsApp group, we can interchange criteria, experience, lesson learned about of the not only H2CM model, if not besides of the other ways, other models, other criteria to so I can to share with this link of the WhatsApp chat for you can join with us. Okay. the next question. How do hybrid systems combining renewable energy with hydrogen production contribute to reducing LCOH? It is depending two key points. Cost of energy supply. For example, in Bolivia, and I think it's same in your country, the cost of the photovoltaic energy, dollars per megawatt hour, is more or less than aeolic cost of energy. First point. Second point is capacity factor. Capacity factor in photovoltaic or solar plant is around of the 30%, 33%, no more. In other side, in the aeolic plant, the capacity factor is around of the 50 or 55%. It's more than solar plant. In this sense, we can to compare and analyze in the model, which is the best option that only solar or only wind or hybrid mix these two renewable options. Okay, we can to see in what percent solar, in what percent renewable. The model can help us to determine which is the best option in terms of the MBA and NMB and the IRR and the payback. The next question. Can the improvements in the lifespan of electrolyzer reduce replacement frequency, lowering the LCOH over the project life cycle? Yes, I know one case that for example, the degradation rate of the electrolyzer is very, very low, and it means that the life cycle of the electrolysis is more than the total life cycle of the project. This is possible. In fact, today, the scientific investigation centers of hydrogen in all countries in the world, and in the many countries, are developing the best option of to down the degradation rate in the electrolysis. So I think this is possible, maybe 1 year more, 2 years more. I don't know, say you it, but I don't know. I know only that it is advancing very fast. I don't know what do you think about it, or in your country, in your region, but from my point of view, it is very, very fast advancing in not only in South America, only Chile country in South America, but in Europe, Spain, Germany, Nordic countries, plus USA, plus Canadian, plus Japan, is advancing very, very fast from my point of view. In this sense, I think this is not the future. This is the reality today, and the countries have to prepare to begin with very strong this competence of the hydrogen ecosystems, hydrogen economy, hydrogen geopolitics included. Okay. Okay. So I think that's we don't have maybe some questions there, Amer. I don't know if you have some other questions to conclude this webinar. I hope you are very clear with the model, with the concept, with the application, and the most important, with the hydrogen is the present. Okay. Thank you so much.
Thank you to you, Engineer Oscar. I would like to say that this was an extremely informative lecture. We've been holding a few lectures this past week, and by far this has to be my most favorite. The amount of work that had to be put to take the model to the place it is right now, and the accuracy it provides is quite outstanding. So thank you for your work on the model itself and on this lecture. And thank you also for everyone who was attending. The last two things I would like to say is for everyone who is attending and would like to have a certificate, we have sent the certificates form on the chat, so please fill that. And another question, Engineer Oscar, is would it be possible to send me the file you were explaining on so I can share it with the rest of the people?
Oh, my pleasure. I can share you my presentation, no problem.
Thank you so much for that. And then thank you again for everyone, especially you, for this amazing lecture. And I hope we will have more webinars in the future.
Oh no, okay, my pleasure there, Amer. And when you want, I with all my pleasure can you share you some experience in your analysis if you want some project of the green hydrogen in study level. I can to support you of the some analyzing of scenarios, ideas. I don't know. So I think I can to help you in if you need some help, some participation in some project that you are developing in terms of the modeling scenarios, etc. Okay.
Of course, thank you so much for that offer. And I hope we will stay in touch in the future. And as I said, maybe arrange more things, more webinars in the future, or as you said, if we encounter any student projects, we'll make sure to ask you as an expert. And hopefully, this would be the start of further collaborations between the AEE, sorry, in Jordan and in Bolivia.
Thank you so much. Okay.
Thank you again. Thank you too.
You have a good day. Okay. My pleasure.
You too. Thank you, and thank you for everyone
Too.
who
Thank you
attended
so much.
today. Goodbye.